To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.
Hello my dear students, welcome to today's lesson. Today I am going to discuss with you all how we can prevent rusting of iron. So you can remember in the previous chapters we discussed the process of rusting. It is also an electrochemical process. Why? Because there is oxidation and reduction taking place. So as you all know, iron undergoes oxidation forming Fe2 plus ions, while water and oxygen, H2O, O2, together they take up electrons undergoing reduction and forming OH minus ions. Fe2 plus and OH minus combine to form FeOH twice, and that further undergoes oxidation with oxygen in air, forming Fe2O3 dot X2H2O. That is ferric oxide with XH2O, that means it is hydrated ferric oxide. That is the brownish color rust. So then we saw different activities where we try to identify the factors that are required for rusting, that is water or vapor and also oxygen in air. Thereafter we discuss some activities where we discuss factors that increase rate of reaction. So you know that both acids and salts increase the rate of rusting, whereas bases decrease the rate of rusting. So those are the information related to rusting that we have discussed before. So today we'll try to understand how we can prevent rusting. Now answer this question. Why do you need to prevent rusting? Or why rusting is disadvantage to us? Because you all know that iron is one of the most highly used metals in our day-to-day life. We use lot of objects or structures that are made up of either iron or steel. If this undergoes rusting, because there's enough oxygen and water vapor or moisture or water in the environment. So if iron undergoes rusting, it can be a huge disadvantage to us. So therefore, we need to prevent rusting, or we have to come up with methods that can prevent rusting. So if we look at the introduction, the speedy corrosion of iron, which is a very useful metal, is a disadvantage. So this corrosion is also a speedy process, somewhat speedy process. Therefore, steps must be taken to control the corrosion of objects made of iron. So, if we want to control corrosion, what do we need to do? Now, you all know the factors that are essential for corrosion. One is oxygen in air and water or vapor from atmosphere. So, if you can cut down at least one of these two factors, if you can remove oxygen, or if you can remove water, or if you can prevent the contact of iron with one of these factors, then we can prevent rusting. So that is what we'll be doing to protect iron from rusting. Control of rusting of iron. What are the methods you suggest to prevent the corrosion of iron? In order to protect iron from corrosion, you may propose that it is appropriate to prevent iron from coming into contact with the essential factors for rusting. It is appropriate to prevent iron from coming into contact with these essential factors of rusting. In fact, if oxygen and water are kept away from iron, rusting can be prevented. For this, following measures can be adopted. If you can keep oxygen and water away from iron, you can prevent rusting. So how can we do that? Now there is enough oxygen in the atmosphere and there is water vapor in the atmosphere. So if you want to prevent it, you have to cover the surface of the iron object with some other material. So to do that, we can apply paint, we can apply grease, or we can apply oil. Now normally, if it is an object made up of iron, you can paint it. So the paint acts as a cover, a protective cover that prevents the contact of air and water with iron. So therefore it prevents rusting. Then in parts, machinery parts, where there are parts in contact with each other which are moving with respect to one another, you all know friction. Now even this friction can increase rusting because the parts are moving one relative to the other. So there what do we do? To reduce friction, we apply grease or oil. By doing that, one thing, we prevent the waste of energy due to friction. In addition to that, we can prevent corrosion. Even oil and grease, they act as a protective layer. They surround that particular object, and because of that, they prevent the entering of oxygen or the oxygen being in contact with iron. Now you can remember when we did the activity where we try to understand that air is essential for rusting. We put a layer of oil over water. So there, that oil layer prevents the air from entering into boiled water. You can remember that. The same way, if you apply grease or oil to a part of a machine, that prevents the contact of oxygen and water vapor in atmosphere with iron. So that is how we try to reduce or prevent rusting. So that is one method. So here we can say the first method, apply paint, grease or oil. So apply paint, grease or oil on this iron object. Here this prevents oxygen and water, that is either moisture or vapor coming into contact with iron. Then there is another method. You can coat iron with tin. Coating of tin on iron objects. Coating of tin on iron objects or objects made of iron. What does this do? A similar function. When you have a coat of tin over iron, that prevents the impingement of oxygen and water or vapor, moisture with iron. So here we can say this prevents the impingement of oxygen and water. Okay, it can be moisture or water vapor on iron. So that is how we can prevent rusting. Two methods. Now one method, we apply paint, grease or oil. So this prevents oxygen and water, that is moisture or vapor, coming into contact with iron. And the second method, coating of tin on iron objects, and this prevents the impingement of oxygen and water, that is, it can be moisture or water vapor on iron. So you can understand this way, students. Now let's say if you have a piece of iron like that. And on top of that, if you have a very thin layer, a layer of tin. So this is iron, this is tin. Sn is tin, you all know that. So when we have a layer of tin over iron, what happens is oxygen is outside here, oxygen and water vapor or water. So they cannot come in contact with iron. So because of that, there will be no rusting. So that is what you have to remember there. Oxygen and water vapor outside, iron is there, but around iron there is a layer of tin. But if this layer gets scratched or removed at a certain place, then of course there is possibility of rusting, or there will be rusting. That is what we have to understand now. You can coat iron with different metals. Not only tin, now you can remember the activity series, students. Tin is below iron in the activity series. But there are metals like magnesium, aluminium, they are above iron. Even zinc is above iron in the activity series. Now all these metals can be coated onto iron in order to prevent from rusting. But if there is a scratch on the surface of this coating, will iron rust or not? That is something you all need to understand. So to understand that, we need to first understand the effect of different metals on rusting. That is what I am going to discuss next. So for that, there is an activity, effect of other metals on corrosion of iron. And to do this activity, there are these materials that are required to us. So first I'll label the materials on this side. So here we need iron nails. Then we need agar powder. Agar powder is needed to make the agar medium. Then we need salt. Salt is sodium chloride, the normal salt that we use at home. We need that. In addition to that, we need phenolphthalein, that is an indicator, you all know that. Phenolphthalein indicator. Phenolphthalein indicator. I will explain why we need to use all these after I write the materials. Then this is potassium ferricyanide. Potassium ferricyanide. Potassium ferricyanide, that is also a chemical substance that we need. Then we need petri dishes. Petri dishes. We need magnesium, because we are looking at the effect of metals on corrosion. Magnesium. Then we need zinc. We need copper. Then there is lead. And also we need water. So here, of course, students, these are the materials. Now iron nails, you all know, because we need to observe the rusting of iron, and we are going to observe the effect of other metals on rusting. And you all know, if we buy these nails commercially, the commercial available irons are usually coated with zinc. So to remove that zinc coating, what do we need to do? We need to soak it in dilute hydrochloric acid for about 10 minutes. Then you need to wash it well, and then you can use it. That is how we need iron nails, and they have to be clean iron nails, not rusted. They have to be very clean iron nails. Then to observe the effect of different metals, we are going to use 4 different metals: magnesium, zinc, copper and lead. And here you all know both magnesium and zinc, they are above iron in the activity series. Both copper and lead, they are below iron in activity series. So these two are more reactive than iron. Copper and lead are less reactive than iron. So we'll be looking at those effects. Then like I said, now we need sodium chloride to make the medium conductive. Because this is an electrochemical reaction, the charges, the ions have to move. So for the movement of those ions, we need to have sodium chloride. That is why we add sodium chloride. Then there is agar. Agar provides a medium. Agar makes a medium jelly-like medium. So you dissolve it in warm water. While the water is boiling, we add agar to it. We dissolve agar in water. So you get the agar solution. And if you pour the agar solution into a petri dish and leave it aside for some time, it will become solidified, but it's not going to be a very strong solid. It would become a gel-like medium. That is where we will be observing the effect of other metals on rusting. So agar medium, you all have to remember these, students. So we need agar provides a solid medium for the observations. Then we need salt, that is sodium chloride, provides ions or charges to facilitate the oxidation and reduction reactions. So that is iron. Then you can remember phenolphthalein. Phenolphthalein. Now what is this phenolphthalein? You all know it is an acid-base indicator. It is an acid-base indicator. Now what does this phenolphthalein do? Normally it is a colorless solution. Even in the acidic medium it is colorless. But in the presence of OH minus ions, it becomes pink. Or it gives a pink color with hydroxyl ions. So it gives a pink color with OH minus, that is hydroxyl ions. So if there is the appearance of pink color, then we know there is OH minus ions. And you all know in the rusting process of iron, when water and oxygen are reduced, there is OH minus ions formed. So to identify where the OH minus ions are formed, we add phenolphthalein to that solid medium. You all know agar provides a solid medium. With that, there will be phenolphthalein. Then we use potassium ferricyanide. Potassium ferricyanide. Now this gives blue color with Fe2+, that is ferrous ions. So this is also familiar to you all. Iron undergoes oxidation during rusting. So Fe becomes Fe2+. So to identify the presence of Fe2+ ions, we use potassium ferricyanide. This gives a blue color with ferrous ions. So that is the reason why we use all these materials. So here, now you can see students, we have all these materials. We use agar to provide a solid medium. Then we use salt to facilitate the oxidation and reduction because salt, Na plus Cl minus, they are charges, ions. Then phenolphthalein to identify the presence of OH minus, and potassium ferricyanide to identify the presence of Fe2 plus ions. In addition to that, we need the Petri dish where we make the medium and have the metals in contact with each other so we can observe the effect, and these are the metals that we are using, and we need water to prepare the medium. So this is what we will be doing. So before that, I will quickly go through these reasons again. So agar provides a solid medium for the observations. Salt, that is NaCl, provides ions or charges to facilitate the oxidation and reduction reactions. Then phenolphthalein, it is an acid-base indicator. It gives a pink color with OH minus, that is hydroxyl ions. And potassium ferricyanide, this gives blue color with Fe2 plus, that is ferrous ions. So this is how we are going to do the activity, students. So this is the method, students. So in this, you all can see here. Now this part. Here, this is the Petri dish. And here it is the agar medium. Agar medium. Then you can see in the first one there is only iron. Then in the second one you can say it says iron and magnesium. So iron nail and magnesium in contact with that. So what we do is we take the clean iron nail. You all know for all these activities, students, if we purchase the iron nail commercially, they are usually coated with zinc. To remove the zinc coating, what do? We soak the iron nails in dilute hydrochloric acid for about 10 minutes and then you wash it off with water. Then the iron nails can be used. So here we have one iron nail, clean iron nail in the first Petri dish. Second one, iron nail in contact with magnesium. So what we can do is we can take a strip of magnesium, just curl it over the iron nail so they are completely in contact with each other, and we set it inside the Petri dish. The same goes for the third one, but where we have iron and zinc. So a piece of metal zinc strip. So that is in contact with iron nail. Then here you can see the fourth one, iron and copper. So copper strip in contact with iron nail. Then we have iron and lead. Lead strip in contact with iron nail. So you get them ready, keep it inside 5 clean Petri dishes. So all that is ready. If you like, you can also label them. First one iron, then iron and magnesium, iron and zinc, iron and copper, iron and lead. Because you all know now copper is reddish brown in color, you can easily differentiate it. But once we pour the agar medium and all, sometimes you might get confused as to what is magnesium, zinc and lead. You can identify, but in case to avoid confusions, if you like, you can label them as well. It is more clear. So that is ready. Then we need to prepare this agar medium. To do that, what we do is we take a beaker. You need to boil water inside that. So water in a beaker, you start heating it, and to that water we add sodium chloride, phenolphthalein and potassium ferricyanide. Now you all know why we need all those. We add them, we mix them together, and once water starts boiling, you add the agar powder little by little so that it doesn't form into clumps. Agar will dissolve completely in boiling water. So once it's boiled completely, then we have the solution ready. But there also you have to remember, students, sometimes now phenolphthalein, because of the mixture, that is a mixture, it is an indicator, because of the constituents, it can vaporize quickly. So in case, just to make sure that there is enough phenolphthalein in the medium, after agar is dissolved completely also, we add a few drops of phenolphthalein. So the mixture is ready. we have all these ready inside petri dishes. You pour the mixture equally into all the petri dishes until the iron and the metals are completely covered with agar. So you have to make sure that happens. That is what we will be doing here. So 5 petri dishes. Now we will look at the method. So here you can see to approximately 250 centimeter cube of water, right? So that is 250 centimeter cube of water. So roughly about 50 centimeter cube of water, the solution for all 5 petri dishes. To that you add a small amount of sodium chloride, phenolphthalein and potassium ferricyanide. Boil the solution, so you have to bring it to boiling and add about 1 teaspoonful of agar jelly to it and stir well. So here we will be adding about 1 teaspoonful of agar jelly. Although here we say jelly, it is the powder that we are adding that will dissolve, and when it solidifies it becomes agar jelly. Then stir well. Take 5 petri dishes. Place only an iron nail into the first petri dish. Keep the strips of magnesium, zinc, copper and lead in good contact with the other 4 nails. So in the first one, only an iron nail. Then strips of magnesium, zinc, copper and lead in good contact with the other 4 nails. That is what I said. If we make it like a loop and cover the iron nail, then it is completely in contact with iron nail. In each of the other 4 petri dishes as shown in the figure. So that is, you need to keep them in each of the other 4 petri dishes as shown in the figure. Then add the hot gel medium. Add the hot gel medium to all 5 dishes so that the nail in each is fully covered. Allow to cool and observe after about 1 hour. Record the observations. So you have to allow to cool it off for about 1 hour and then you need to observe. So you need to wait till about an hour or slightly sometimes more time, or sometimes before 1 hour you can start observing the color change. So that is what we do for this particular activity. So you make sure you have all the metals in contact with iron and the agar gel medium with all the other components completely covers the iron nail and the metals in all 5 petri dishes. Then we let it to cool and we observe. So that is the activity, students. Now let's go to the lab and do this activity now. Okay, students. So now I am going to do this activity to observe the effect of other metals on corrosion of iron. To do the activity, we have a lot of materials that are needed to us. Now I have a beaker with water, about 250 milliliters of water, and then I have a spirit lamp. You can use a Bunsen burner as well in order to boil the water and prepare the mixture. So we have a glass rod as the stirrers. We need to mix the solution with the contents being added to it, so that it doesn't clot or become solidified. It has to be a uniform mixture. So to do that, I have the glass rod there. Then I have the rest of the materials here. You can see phenolphthalein is an indicator. You are familiar with acid-base indicators. Now phenolphthalein is a colorless solution that turns pink color in the presence of OH- ions or bases. So phenolphthalein is an indicator. Then I have potassium ferricyanide solution. Now here you can see this is potassium ferricyanide solution. Now the use of potassium ferricyanide is that in the presence of Fe2 plus ions, that is ferrous ions, when there are ferrous ions, potassium ferricyanide gives a blue color. So now you are familiar with the process of corrosion, rusting. Now there is iron, Fe, it loses electrons, undergoes oxidation and becomes Fe2 plus ions. So when that happens, when there is Fe2 plus ions in the medium with potassium ferricyanide, there will be the appearance of blue color. Then we have sodium chloride here. Now, sodium chloride is also added to the mixture. It provides ions. Now, you all know normally sodium chloride accelerates rusting, or the reaction of rusting is facilitated by the presence of sodium chloride salt because they have ions. Sodium chloride ionizes easily. So, that is the function of sodium chloride. Then we have agar. Agar, this is the agar powder. Now, you all are familiar with this. Agar can become like a jelly-like substance. Now, when you add agar into hot water or boiling water and mix it well, it dissolves. But if we pour it into a container and let it to stand for a few hours, it solidifies and becomes like a agar jelly, gel-like medium. So, that is the purpose of using agar. Then I have the different metals. Now, here you can see I have 5 similar size iron nails there and different metals. Now, these are the iron nails. You can see that. Then I have different metals here. I have magnesium. Then we have zinc metal, then I have copper metal, and I have lead there. 4 different metals. So, what I'll be doing first is, I'll be setting these iron nails inside these 5 petri dishes. Now, I have labeled them as well. Here you can see the first petri dish, it's only going to have the iron nail there. Then, the second petri dish, it's iron and magnesium. So, I'll be placing the iron nail and on that I will have to place the magnesium so that it is very much in contact with the iron nail. You have to place the second metal so that it is very much in contact with iron. Then I have iron and zinc, the third petri dish. So, here iron and zinc. You can see the iron nail, the zinc is touching the iron nail. I have actually folded one end of the zinc, the other metal, so that you can pass it through the iron nail. So, they are completely in contact with each other, iron and zinc. Then we have iron and copper. The same way, I will insert the iron nail through copper and place it like that. So, iron and copper. And the last one is iron and lead. Iron and lead. Iron and lead. So, here we have iron and lead. So, this is how we have the 5 different petri dishes. First one, only iron, that is to confirm that there is rusting taking place. And here in all 5 petri dishes, we have iron nails which are very clean, similar in size and shape. So, 5. First one only iron, second one iron and magnesium, third one iron and zinc, then we have iron and copper and iron and lead. Now, you all can remember the activity series, students. Magnesium and zinc, they are above iron in the activity series. Copper and lead, they are below iron in the activity series. So, that is how we select these 4 metals. Now, we have to prepare the medium, the agar medium. To do that, now first I'll need to boil water. When it is becoming hot, we will add sodium chloride, potassium ferricyanide and phenolphthalein into water. And we have to bring it to boiling point. Now there is something you all have to remember, students. Although according to the procedure, we add phenolphthalein into water and then boil it. But the thing is, phenolphthalein has the tendency to quickly evaporate off due to its composition. So, because of that, while boiling, sometimes we can lose a small amount of phenolphthalein or all the phenolphthalein because we are adding few drops. So, to compensate for that, what I will do is, after mixing the agar also, I will add a few drops of phenolphthalein to the mixture. So, to that, I will need to add this yogurt spoonful of sodium chloride would be enough. That. and a few drops of potassium ferricyanide and also a few drops of phenolphthalein. So to water I have added sodium chloride, potassium ferricyanide and phenolphthalein. Right. Now we need to mix it so that these substances dissolve well, and also we need to bring it to boiling point. Need to allow it to boil. Until it boils, I'll keep all these to a side. So now you can see the water starting to boil. But we need to bring it to boiling itself before I start adding the agar. We'll let it to boil for some more time. So just to recall what we did, into about 250 milliliters of water, I added 1 yogurt spoonful of salt, that is sodium chloride, so that it provides ions to the medium. And also you all know, normally salts, because of the ions, they accelerate or increase the rate of rusting. So they facilitate the anodic and cathodic reactions. And also we have potassium ferricyanide in order to give color, blue color, when there is Fe2 plus ions present. So if iron nail undergoes oxidation, then potassium ferricyanide will give a blue color. And the addition of phenolphthalein in order to observe the formation of hydroxide ions. When there are OH minus ions, phenolphthalein gives a pink color. And now I will have to add the agar. Here you can see the agar powder is there. If I add that and make a solution in hot water, boiling water only, agar will dissolve well and we will get a homogeneous mixture. After that, when we pour the agar into all these 5 petri dishes, it will solidify. That will take about at least an hour to do, hour for the agar to solidify and give a gel-like medium. So still we need to allow the solution to boil properly. So in this there is water, potassium ferricyanide, sodium chloride and phenolphthalein. Okay students, so it's almost closer to boiling. Then I will start adding the agar. You have to add little by little while mixing it completely. Otherwise, the agar will solidify in clumps. That is not very useful for us. It has to dissolve completely. You have to add agar little by little and make sure it dissolves. We need to add about 1 teaspoonful of agar. So that is what I have taken here. So now that I have transferred all the agar powder into it, we have to mix well so that it dissolves completely. So now that the agar is completely dissolved, we have our mixture ready. I will have to take it off from the burner and then I'll have to pour it into the petri dishes. So now we have the mixture ready. You all know what the contents are. Water with potassium ferricyanide, phenolphthalein and sodium chloride salt. Thereafter, I added agar and the agar has dissolved completely. So there is no clumps of agar or any solidified particles there. I can pour them into the 5 petri dishes here. So while pouring, it's better if I can keep the glass rod and pour it onto that so that the solution doesn't spill. So that is for the iron nail. We have to make sure the metals are completely covered in the solution. So then the next one, iron and magnesium. Then we have iron and zinc. Then I'll pour into iron and lead. And then here we have iron and copper. We have to make sure the metals are all immersed inside the mixture. Now here you can observe, students, while I poured the solution itself, you can see the formation of the color, the pinkish color around iron nail. But the others, of course, we cannot see the color change. Anyway, we will have to wait for about at least 1 hour until the agar solidifies and until the changes take place. So what you need to observe is the appearance of pink color, appearance of blue color, whether they are there, and if they are there, around what metal is the color present. So you have to look and see whether there is blue color near the iron nail or pink color near the iron nail or the metal. Those are the observations that you have to look for. So we will observe this after 1 hour. Okay, students. So you all have understood how we made the activity, how we prepared all these petri dishes containing the 2 different metals. So as you can see here, it's only the iron nail. And you can remember, to the agar medium, what did we add? We added the phenolphthalein indicator, which gives a pink color with hydroxyl ions, as well as the potassium ferricyanide that gives a blue color with ferrous ions, Fe2 plus ions. So if we look at the first setup here, that is only the iron nail. Can you see here at the 2 ends of the nail? You can see the blue color regions clearly, but in the middle you can see the pink color is faintly visible. So what has happened here? At the 2 ends, iron has got oxidized and the Fe2 plus ions have been formed that give the blue color with potassium ferricyanide. Whereas in the middle, water and oxygen react together and undergo the reduction reaction that forms the hydroxyl ions. So that gives a pink color with phenolphthalein. Can you all observe that clearly? You can see it here as well. So this is only iron. Then we use different metals to protect the iron. That is what we wanted to observe. So here you can see the first 2. The observations are similar. That is the first, this setup with iron and magnesium metal. Magnesium is above iron in the activity series, as well as iron and zinc. Zinc is also above iron in the activity series. Now observe what has happened. Can you all see the colors, students? Here you can see the pink color near the iron nail. And there is no blue color formed in the medium. So that means only OH minus have been formed near the iron nail, and there the iron nail has acted as the cathode, because the formation of OH minus is the reduction reaction. But there is no change in iron. The same thing here. When there is zinc, oxidation takes place at the zinc, and reduction of water and oxygen forming hydroxide ions take place near the iron electrode. So there again iron has become the cathode. So in these two, where we use magnesium with iron and zinc with iron acts as the cathode. So we call that method of protecting iron as the cathodic protection. And here magnesium and zinc are the sacrificial electrodes. They sacrifice themselves to protect iron from corroding. Now if we come to the last two activities, here you can see iron and copper. Copper is below iron in the activity series. The same way iron and lead. Lead is also below iron in the activity series. Observe the changes here. You can see near the copper plate there is pink color. That means OH minus ions have formed there, and that is the cathode. Whereas here near the iron nail you can nicely see the blue color region. That is due to the potassium ferricyanide reacting with ferrous ions. So that means iron has acted as the anode. So copper is the cathode, iron is the anode. The same way with lead and iron. You can see near the lead plate again there is pink color. So presence of OH minus ions, that means the lead has acted as the cathode, and near the iron you can see blue color, that is the presence of Fe2 plus ion. So that is the anode. So in these two instances where we use copper and lead, if there is a full coating over iron, then the oxygen is not in contact with iron and iron doesn't corrode. But if there is a scratch, and if iron is exposed to oxygen and water vapor, what will happen is both the copper and lead will act as the cathode, and iron will undergo oxidation. It will act as the anode, so it will undergo corrosion more. So the best way to protect iron is to use either magnesium or zinc. So those are the sacrificial electrodes. So can you all understand the observations clearly, students? Again, you all can look at the colors clearly. Iron nail only, iron and magnesium. Near the iron it's only pink color, iron and zinc. Again near iron it's only pink color, so that is the cathode. And here when it is iron and copper, iron reacts as the anode, and again with iron and lead, iron reacts as the anode. So those are the ways of protecting iron from corrosion. Okay, students. So I'm sure you would have seen all the observations clearly. Did you see the different colors, the pink and blue color at different places, either near the iron nail or the other metal? You were able to see the appearance of different colors. So that was the observation we got. If we try to understand that again. So in the first petri dish where we had only the iron nail, you were able to see the regions. There was the appearance of pink color as well as blue color. So you all know pink color means there are OH minus ions, because pink color is given by phenolphthalein. Phenolphthalein in the presence of OH minus ions gives a pink color. So here there will be pink color. Now here students, in addition to the observation, I'll give you the explanation as well. So here there will be pink color. Then the two blue color regions, potassium ferricyanide gives blue color in the presence of Fe2 plus ions. So here it is going to be Fe2 plus ions. This is the agar medium in the petri dish. So that is how you got the observation in the first petri dish. So here there has been oxidation of iron. Fe has become Fe2+. That is why Fe2+ gave blue color with potassium ferricyanide. At the same time, oxygen, water take up electrons and become OH- ions. That is the reduction reaction. So both oxidation and reduction taking place during rusting have taken place in the first petri dish. That you all can understand. Then in the second one. Now look at the second one. There you were only able to see pink color near iron. Near iron, pink color. Near iron, pink color. So there is OH- ions near the iron nail. And there is no blue color. So what is the meaning of that? No blue color. That means no Fe2+ ions. So in this petri dish where we had iron and magnesium, there was no formation of Fe2+ ions. That means iron has not been oxidized. But the reduction, that is the presence of OH- is seen near iron. So that is caused by the reduction reaction that has taken place near the iron nail. Same thing here. In both of these, it's the same. Here also there is Fe near iron, you get the OH- ions. That is why the pink color region. And there is no blue color. That means there are no Fe2+ ions. That means iron has not been oxidized. So if reduction has taken place, there should be a species that has undergone oxidation. What is it? It is the other metals here. In this one magnesium, in this one zinc. Both zinc and magnesium have undergone oxidation. Can you all relate that to the activity series? In the activity series, both magnesium and zinc are above iron in the activity series. That means they are more reactive than iron. Iron is less reactive than magnesium and zinc. So therefore, iron does not undergo oxidation. Both magnesium and zinc in these two petri dishes undergo oxidation, whereas reduction takes place near iron. That is why you don't have the blue color, but you get the appearance of pink color near the iron nails. Is that clear, students? So in these two, 2 and 3, if I write the explanation, so here in dish 1, appearance of blue color means iron has undergone oxidation. That is, Fe solid becomes Fe2+ aqueous, losing 2 electrons. That is in the first dish. At the same time, water and oxygen react to form OH- ions that give pink color with phenolphthalein. So here, of course, both reactions of rusting have taken place. But if you take petri dish 2 and 3, 2 and 3, there what happens? No blue color. That means no oxidation of iron. Pink color near iron nail means reduction has taken place near the iron nail. That is formation of OH minus ions. It is the formation of OH minus ions. So that has occurred near the iron nails. So what undergoes oxidation? So in 2, magnesium gets oxidized. That is, Mg solid becomes Mg2 plus aqueous by losing electrons. And in 3, zinc gets oxidized. How does that happen? Zinc solid becomes zinc 2 plus, losing electrons. Why do that occur like that? Because both magnesium and zinc are more reactive than iron. So that is the important thing. Both magnesium and zinc are more reactive than iron. Therefore, they get oxidized and reduction occurs near iron. This prevents iron from rusting. And this method is known as cathodic protection. So you have to understand these, students. In the first petri dish, like I said here, in dish 1, appearance of blue color means iron has undergone oxidation. This is the reaction. And water and oxygen react to form OH minus ion that give pink color with phenolphthalein. So that means both the reactions, oxidation and reactions related to rusting, have taken place in the first petri dish where there was only iron. That is to show that rusting is taking place during this activity, to confirm that. Then in the second and third petri dishes, you saw similar observations. There in the second one we had magnesium in contact with iron, third one zinc in contact with iron. There was no blue color, that means no oxidation of iron, no Fe2+. Pink color near iron nail means reduction has taken place near iron nail, that is formation of OH minus has taken place near iron nails. So from that, what can you understand? In the second one, because there is no oxidation of iron, it should have been magnesium that got oxidized. Magnesium gets oxidized. This is the reaction. Mg solid becomes Mg2 plus aqueous, losing 2 electrons. And in the third one, zinc gets oxidized. That then becomes zinc 2 plus, losing 2 electrons. So from this, what can we understand? Both magnesium and zinc are more reactive than iron. That is in the activity series, you can remember. Therefore, they get oxidized and reduction occurs near iron. So this prevents iron from rusting. And when reduction occurs near iron, we call iron as the cathode. So iron becomes the cathode, the other metal becomes the anodes. So because of that, this particular method of preventing rusting by having either magnesium or zinc in contact with iron is known as cathodic protection of iron. And in this method, both magnesium and zinc kind of sacrifice themselves to protect iron from rusting or to prevent iron from rusting. Therefore, both magnesium and zinc are known as sacrificial electrodes. You have to remember that term. Both zinc and magnesium are known as sacrificial electrodes because they are sacrificed to prevent iron from rusting. These two metals undergo oxidation and make the iron the cathode. So that method of protection is also known as cathodic protection. So that is for the second and third petri dishes. Now we will look at the fourth and fifth petri dishes. The fourth and fifth ones. Now here, look at the changes there. You can see blue color near iron. Here also you can see blue color near iron. What is the meaning of that? Appearance of blue color means iron Fe2 plus ions are present. So that means iron has undergone oxidation. Fe has lost 2 electrons forming Fe2 plus ions. Iron has undergone oxidation. So there iron will be the anode. At the same time, you can see pink color near copper and pink color near lead. So there are OH minus ions formed near copper and lead. And OH minus forms due to the reduction of water and oxygen with electrons. Both water and oxygen together take up electrons and get reduced to form OH minus ions. That happens near copper and lead. So that means in this copper and in this one lead acts as the cathode and iron acts as the anode. So that is what you need to understand here. So this is one, then pink color near copper and lead. Lead is Pb. So that is the observation. So from that, what can we understand? Iron undergoes oxidation, so iron acts as the anode. Both copper and lead, they don't oxidize, but reduction takes place near them. So that is because both copper and lead are less reactive than iron. That is what you need to remember here. So in this one, if we try to understand the observations in Petri dishes 4 and 5. Blue color confirms the presence of Fe2 plus ions. That means Fe solid undergoes oxidation forming Fe2 plus using 2 electrons. So here oxidation occurs at iron. So that acts as the anode. At the same time, pink color, so here first one blue color, then pink color near copper, we can say dish 4, and near lead in dish 5 confirm the presence of OH minus ions. That means what? You can remember the equation 2H2O plus O2 gas plus 4 electrons giving rise to 4OH minus ions. 2H2O liquid, O2 gas plus 4 electrons give rise to 4OH minus ions. That is the reduction reaction. Reduction reaction occurs near copper and lead. That is copper and lead act as cathodes. What is the reason? Because both copper and lead are less reactive than iron. They are below in the activity series. So that is what you need to understand here. So in this, in Petri dishes 4 and 5, blue color confirms the presence of Fe2 plus ions. So that means Fe solid has undergone oxidation, forming Fe2 plus, losing electrons. Oxidation occurs at iron that acts as the anode. At the same time, you can see pink color near, this should have been near, it should be near, pink color near copper in dish 4 and near lead in dish 5. Confirm the presence of OH minus ions. So what is the reaction? 2H2O liquid plus O2 gas plus 4 electrons give rise to 4 OH minus aqueous. So there, what happens? This is the reduction. Reduction occurs near copper and lead. That means that copper and lead act as cathodes. And what is the reason? Because both copper and lead are less reactive than iron. So if we try to understand this concept. Now here we have magnesium, then we have zinc, then we have iron, and we have lead, and then we have copper. So if you have magnesium and zinc to protect iron, both magnesium and zinc more reactive than iron, then iron is the cathode. So we call it the cathodic protection. And magnesium and zinc are known as sacrificial electrodes. Magnesium and zinc, sacrificial electrodes. So this is like a summary, students. It's important for you all to remember this. So if you coat iron with zinc or magnesium. Now I told you all earlier, even if the coating gets scratched and iron is exposed to the atmosphere, still magnesium and zinc will get oxidized. Iron will act as the cathode. So therefore, the cathode ion will be protected. This method is used in ships, hulls of ships, where it is a very large structure, the sea, salt, so high chances of rusting. What they do is they have small pieces of magnesium inserted between iron. So magnesium will be the sacrificial electrode and iron will be the cathode and it will be protected. Same in huge structures like bridges made up of iron or steel. They place small pieces of magnesium or zinc there. They are also, the magnesium and zinc will act as the sacrificial electrodes. Because of that, iron will be protected. And time to time, you can just replace this magnesium or zinc. Even in galvanizing. Galvanizing, zinc is coated onto iron. So there, initially, when the coat is there, the coating prevents the contact of water and oxygen with iron. Therefore, there will be no rusting. But even if the coating gets scratched, still no problem. Iron will not undergo rusting. But if you look at the other two metals, now you all know sometimes they coat lead or copper onto iron. Even metals like nickel and all that, they are coated onto iron. So what happens is, if we consider this, lead and copper. So here, lead and copper are less reactive. They act as the cathode, and iron is the anode. So, if you have an instance where you have, let's say, a small object made up of iron, and onto that we have a coating of copper coating. So here what happens? When there is the copper coating, there is no contact of oxygen and water with iron. So O2 and water are not in contact with iron. Therefore, there will be no rusting. But, very important, if there is a scratch, then what happens? Now we have the iron there. Now we had the copper coating, but the copper coating is scratched at a certain place. This is the copper. Here iron is exposed to both air and water. Then what will happen? Copper will be the cathode and iron will become the anode, and both O2 and water are there. So what will happen? There will be rusting. So that is something you all have to remember, students. If you coat iron with a metal that is above iron in the activity series, then iron will be the cathode. Even if there is scratching of the coating, there will be no rusting. But with metals like copper and lead, both metals like copper and lead, which are less reactive than iron, they act as the cathode and iron will be the anode. So until there is a layer over it, completely coated with copper, that is by electroplating, you can electroplate copper onto iron, we have discussed that. So if it is an electroplated object, until the copper plating is there. So here it is coating or actually plating. The copper plating is there. There will be no rusting because oxygen and water are not in contact with iron. But therefore, there will be no rusting. But if there is a scratch, here you can see if there is a scratch, then of course copper will become the cathode, iron will be the anode. Why? There is oxygen and water in contact with iron and there will be rusting. You have to remember that. Is that clear to you? So this is the effect of other metals on rusting. Metals that are above iron prevent iron from rusting. Metals that are below iron, they actually act as the cathode and they kind of facilitate rusting if iron is exposed to oxygen and water. You all have to understand that concept. But still, we do plate iron with copper or other metals which are below copper in the activity series. Silver plated, copper plated, gold plated. So all that is carried out. As long as the plating is complete, there is no problem. But if that gets scratched, then there will be rusting. You have to remember that, student. Is that clear? So with that, I'll move on to the next slide. Again, we will discuss the observations and the reactions related to the observations. So here, in the Petri dishes 2 and 3 above, pink color is seen around the iron nails. That means OH minus ions are formed near the iron nail. Absence of blue color show that Fe2 plus ions have not formed. So you have to remember that also. Absence of blue color show that Fe2 plus ions have not formed. In the Petri dishes 2 and 3, the iron nails are in contact with magnesium and zinc, which are more reactive than iron. Hence, cathodic reaction has occurred at the iron nails. So, near the iron nails, what is the cathodic reaction? 2H2O liquid plus O2 gas plus 4 electrons, giving rise to 4OH minus aqueous. That is the cathodic reaction. Here, the metals of higher reactivity, magnesium and zinc, act as the anode. So, you have to remember that. Metals of higher reactivity, magnesium and zinc, act as the anode. At these metals, oxidation occurs. So, their oxidation occurs. So, what is the oxidation process? One is magnesium solid becoming magnesium 2 plus, losing 2 electrons. At the same time, we have zinc solid becoming zinc 2 plus aqueous by losing 2 electrons. So there you can see. The magnesium 2 plus and zinc 2 plus ions formed do not give a color with potassium ferricyanide. Very important. Magnesium 2 plus and zinc 2 plus that are formed do not give a blue color with potassium ferricyanide. All what we discussed, so I'm sure you all can understand that. Then I'll move on to the next slide. Then here, appearance of blue color around the iron nails in the Petri dishes 4 and 5 indicates the formation of Fe2 plus ions. This shows that the iron nails in them have corroded. In these setups, iron acts as the anode and is subjected to oxidation. So, if we write the reaction, Fe solid becomes Fe2 plus aqueous, losing 2 electrons. So, iron is the anode there. Then, you can see copper and lead are placed below iron in the activity series. When iron is in contact with such a metal, iron rusts faster. That is very important. When iron is in contact with such metals, iron rusts faster. That is why what I explained to you all. If the plating is scratched, then the rusting occurs faster. Areas around copper and lead strips turning pink indicates the formation of OH minus. So, around copper and lead strips turning pink indicates the formation of OH minus ions closer to them. Therefore, the following reaction should have occurred at copper or lead. What is that reaction? 2 water molecules with O2 gas taking up 4 electrons, giving rise to 4OH minus aqueous. So, that is the reaction taking place near copper and lead. I am sure you all can understand these also, students. I have explained all these in detail in the previous slide with the observation. So, then I'll move on to the next slide. According to the above observations, it would be clear to you that in order to protect iron from corrosion, a metal above iron in the activity series can be kept in contact with iron. So that is something you have to remember. So in order to protect iron from corrosion, a metal above iron in the activity series can be kept in contact with iron. Then iron acts as the cathode and it's protected from corrosion. Protecting iron by making it the cathode of an electrochemical cell is known as the cathodic protection or sacrificial protection. Cathodic protection because iron acts as the cathode. Why do we call it sacrificial protection? I told you all, they are both magnesium and zinc act as the sacrificial electrode. They undergo sacrifice or they do a sacrifice to protect iron. They undergo oxidation to protect iron from rusting. So that is what I explained to you all. So here instances where cathode protection is used. So when we say cathode protection, you have to remember students, the metals above iron in the activity series or metals that are more reactive than iron have to be used. So examples, magnesium, zinc, those are more reactive than iron. So here one method is coating zinc on iron objects. That is known as galvanizing. Galvanizing. I have told you all this. Examples, we can consider the buckets, iron buckets that are galvanized. Buckets used to carry water, draw water from the well. Even the iron nails we have talked about, those are coated with zinc. Buckets, nails, then barbed wires, roofing sheets, and also we can consider GI pipes. GI pipes. When we say GI pipes, it means galvanized iron pipes. So coating zinc on iron objects, that is known as galvanizing. Now these are done for buckets, water carrying buckets, then iron nails, barbed wires. You all know what barbed wires are. They are used in fences as rolling wires for protection. They use barbed wires. Then roofing sheets that are used as roofs, and GI pipes, those large pipes that are used to transport liquids. The GI pipes, galvanized iron pipes. Now in all these, there is a coating of zinc over the iron metal. How they do this is, they heat zinc to a very high temperature so that zinc will melt and it will become the liquid, and there will be a container or a tank with zinc liquid in it. Into that, they submerge the iron object. So in this process, they dip or submerge an iron object inside a molten zinc liquid. That is known as hot dip galvanizing. A process called hot dip galvanizing. So I will write that also here just for you all to remember. This process is known as hot dip galvanizing. Not electroplating. We have in an activity, we saw how we can plate zinc onto iron, but we don't use that method here. Here it is not electroplating, it is known as hot dip galvanizing. So there is a liquid of zinc. Into that you submerge the iron object and the zinc coating gets applied onto the surface of iron. Is that clear? So that is one method of preventing iron from rusting using the cathodic protection method. Then the other one, welding blocks of magnesium or zinc into hulls of ships in the sea. So like I told you all students, this is to protect the hulls of ships. So what do we need to do? Both the zinc and magnesium can corrode with time. Therefore, time to time we need to replace them. So the zinc and magnesium needs to be replaced from time to time. You can remember students, when we discuss magnesium, we have discussed this application or use of magnesium not only in hulls of ships, even in long pipelines, long iron pipelines, oil pipelines, as well as in large structures like bridges. They use the same method. So that also is something that you need to remember. The same method is used in iron or steel bridges and steel pipelines. So you have to remember that as well. So these are methods of protecting iron from plastic, that is cathodic protection. Coating zinc on iron objects, galvanizing, that is hot dip galvanizing, not electroplating. Example, buckets, nails, barbed wires, roofing sheets and GI pipes. Then there is welding blocks of magnesium or zinc into hulls of ships in the sea when they are sailing, and the zinc and magnesium needs to be replaced from time to time because they undergo oxidation. And the same method, like this welding of magnesium and zinc, is done used in iron or steel bridges and steel pipelines. So you have to remember that, students. So with that, students, I have actually completed this lesson and I am going to end this chapter at this point. And in the next chapter, I will discuss the summary with you all, and thereafter I will discuss the questions given in your textbook.
To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.